In this recording, we're going to look at chapter 16, which is on earthquakes. And so we will do our screen share. Hopefully everybody can see the same thing I see. All right, so earthquakes, what causes them? Anything that shakes the ground you walk on is going to cause an earthquake. Some earthquakes happen close to the surface. They can be triggered by dynamite at a building site. But most of the time when we think of an earthquake, it's because there has been some release of energy deep underground, and that has shaken the rock. Again, it could be half a mile, 2 miles, 10 miles or more underground. And then that vibration reaches the surface of the earth, and we call it an earthquake. So earthquakes are sometimes called seismic waves. They happen, again, primarily along fault lines. It'd be nice if we knew where all the fault lines were, but we don't. Sometimes the movement is in a process that we sometimes call the elastic rebound process. So that's when a rock reaches its limit. You bend it and bend it and bend it, and it just can't bend anymore. And there's a rapid release of energy, and it's like you stretch a rubber band and it pops. The second theory is called the weak fault model, and in that one, very little energy is required to trigger the earthquake. We think that sometimes happens when there's motion between faults that are maybe almost horizontal to each other. That seems to be a more probable result. And then we have it because there's just sticking along a fault, and then when there's finally enough energy for the two sides to move past each other, they do, and you end up with an earthquake that way. You could also have earthquakes associated with volcanic activity. That's really quite common. A volcano erupts, and there's also an earthquake to go along with it. So let's look at some of these seismic waves. When we're talking about an earthquake, we talk about the focus and the epicenter. So you can see in the little graphic that the focus is where the energy is first released. That's the origin of the earthquake. The epicenter is the place on the ground directly above that. And so if they say that an earthquake had its epicenter in Lenoir, North Carolina, then that's not where the original energy is released. It's down below that. But they give us the epicenter because it gives you some point of reference that's meaningful. We've got two types of waves that are released from Earth as a result of earthquakes. They're body waves and surface waves. So body waves travel through the interior of the earth, and surface waves, of course, travel on the surface. Under body waves, we have two subcategories. You can have P waves and S waves. The P waves, which are sometimes called the primary or the push waves, arrive first at a recording station, so they travel the fastest. They are a compression wave like sound is. And they also travel through both rock and fluid. An S wave is a secondary wave or a shake wave. They are a little slower, and they will travel through rock, but they don't travel through gases and liquids. So a geologist can tell a P wave from an S wave not only by their arrival times, but it also can help them tell what kind of mineral they had to pass through to get there. If you see the P wave, but you don't see the S wave, and then it pops up again, it's probably because there was a natural gas or oil deposit that the wave had to travel through. So S waves also shake the ground differently. So P waves are compression waves like sound is, but an S wave is a shear wave like you shake a rope or a water wave. So they're very different. So we said we had surface and body waves. We've talked about the body waves. The surface waves are different. They are the slowest waves set off by your earthquake. They travel along the surface, which makes them really the most dangerous as far as humans are concerned, because they do the most damage to buildings and to the ground. We have different categories that we divide these surface waves up into. We have love waves and Rayleigh waves. A love wave shakes the ground from side to side, and they don't travel through liquids, but they do knock down buildings off their foundations. A Rayleigh wave acts like a rolling sea wave, so the ground goes up and over in sort of an undulating motion, and they are also very destructive. We've got a little graphic we can look at. So if we have undisturbed material, it looks like this. If you have a P wave, a primary wave, the ground is going to be compressed from side to side. So you can see it's closer here and farther apart, closer and then farther apart as the energy moves through it. It compresses the rock, and then it's that compressive energy that moves along, kind of like you gathered up a spring and released it. So that's a P wave. An S wave, we said, was like a water wave, so up and down and up and down and up and down as it travels through. And then we had the Rayleigh and the love waves. Rayleigh waves, I said, were like, again, ocean waves, so up and over, shaking the ground. And love waves are a back and forth motion. Okay, to give you some idea of what those might do on the surface of the earth, if this first little block represents the ground undisturbed, and now the one on the right of it is a P wave, this is the kind of damage you would expect to see. So maybe your fence is damaged a little in one spot, and then you go a ways, and then it's damaged again. If it's an S wave, the whole thing sort of moves back and forth. And if it's a surface wave, not only does it, it goes up and down in that undulation. So differences that a geologist could pinpoint. So how do we locate and measure earthquakes? Well, there's a lot going on with that. So we use something called a seismometer. There are various types, but basically this is a device used to record the motion of rock in the vertical direction. So one way you could do that is have some sort of marking pin on a weight. So it's on a spring. I know it looks a lot like a pendulum, but this goes up and down. So if the ground shakes, the pin shakes, and it causes the pin to make a mark on the paper, and the paper is a rolling drum. So they have a recording over time of what's gone on in the area. Now, in reality, this is not used very much anymore. We don't rely on pins, on rotating drums and paper trails. A lot of it is, there's still devices that shake, but when they shake, they create an electrical signal, and that signal is sent up to a satellite. And then the satellite relays it to a processing center. And it's stored on a computer someplace. This is again another version of our seismometer. You can see you've got a little lever coming out, and it'll wiggle over time. And you can tell by the photograph, this is really old. So the seismograph is just a seismometer with some sort of recording device attached to it. Alrighty, so what would we get, whether we looked at it electronically on a computer or on a piece of paper? You would see a tracing, and then there'd be a little mark, that would be the P wave, and a little bigger mark would be the S wave, and then an even bigger mark would be the surface wave. So your seismogram ends up looking something like this, where if we know that it starts here, this is the fastest, it got there first, and then the S is a little bigger and comes in the middle, and the surface wave is the biggest yet, but it's also the last to arrive. There's another version of this. So the P wave arrives, and then here's your S wave where there's a time interval, and then the surface wave. The time intervals are important because the longer the time interval, the farther away the earthquake is from your location. If you are almost on top of the earthquake, even though the P and the S travel at different rates, they won't be very far apart. But if you are a long way away, the P will get there first, and then you'll have to wait, and then the S wave, and then finally the surface wave. So the bigger the time gap, the farther away you are from the earthquake itself. And here's just another view of things. I have seen a few of these, and they are really hard to interpret if you don't know what you're looking at. You're never as cleaned up as these drawings are. So we've talked about how the P and the S and the surface waves start out at the focus at the same time, but they travel at different rates, so they arrive at different times. And I've mentioned that the closer you are to the station is to the earthquake, the closer these waves are going to be on your seismogram, and the farther away, the farther apart. And so that leads us to travel time curves, which would look something like this. So they might plot the P wave and then the surface wave, and they're looking at this gap between them because they've got time on the vertical axis. And the bigger the gap, the farther away you are. To locate the epicenter, you have to have readings from at least 3 recording stations. You can have more than that, but you can't do it without a minimum of 3 recording stations. If we look at our little map of the United States, the blue circle you see is information from a recording station in Charleston, South Carolina. The red circle is from Detroit, Michigan, and the green is from Minneapolis, Minnesota. So if you just looked at the blue one, you would know how far away the earthquake was. You just wouldn't have any idea of which direction. A recording station can tell you the distance you are from the epicenter, but it does not tell you in which direction. So if we just had the blue circle, we've got a whole lot of places to pick from. If you added Detroit to the mix, Detroit, where the 2 circles overlap, are possibilities. So if Detroit and Charleston are measuring the same earthquake, then where they overlap, where their circles overlap, those are your choices. So with 2 circles, you get 2 places where they overlap. You can see we got this spot right here, which is kind of west of New Jersey. I'm not really sure where it's supposed to be exactly. Maybe Maryland? This is Maryland up here, someplace in Maryland. And then there's another one right here. So this is North Carolina, Tennessee, here's Kentucky. So somewhere in the way western part of Kentucky. So if we add in the green recording station from Minneapolis, it overlaps with Detroit in 2 places, here, someplace up in Canada, and then down here. And in fact, it's this spot right here where all 3 circles overlap. That's your epicenter. And this is a spot actually in a place where you get quite a few earthquakes. It's called the New Madrid Fault. And a lot of earthquakes have happened in that area. Charleston, South Carolina has actually had an earthquake too, a very big one back in the 1800s. All right, in the lab we'll do, you will have a tracing, and we'll look at the amplitude. How high above the midline do these markings go? And we'll look at the difference in the S and the P times, and we'll plot the time, and we'll plot this amplitude on this special kind of graph. This special kind of graph, let's see, did I talk about it? I guess I didn't. I apologize. On this special graph, and where they cross the middle line will give us the amplitude or the magnitude of our earthquake. We'll do more with this in lab. I just wanted you to say, earthquakes when you see it. We'll see it again, I promise. So let's look at earthquake strength. So there are two ways we measure the strength of an earthquake. We use the Mercalli scale or the Richter scale. The modified Mercalli scale determines the intensity, and it uses it to measure, it's based on the effect that the earthquake has on people and buildings. It uses Roman numerals 1 to 12 and is a really good scale if you are the Red Cross and you want to know what kind of supplies to send in. The Richter scale looks at energy released and gives us a magnitude. Now on the news, they always give you the Richter scale, but that really doesn't tell you, did the whole town collapse? Are there thousands of people dead? You can have a 7 on the Richter scale earthquake in California, and nobody may die. You can have that same 7 in Iran, and 50,000 or 100,000 people could be dead. Or in China, 100,000 people could be dead. And it has to do with the differences in building codes and how closely people live together and what kind of warning systems are in place. So it's all about lifestyles and building structures and community response. But in those cases, those 3 locations, you would have 3 different Mercalli scale ratings for those 3 locations, even though they might all 3 have the same Richter scale designation. So the Richter scale is not linear, it is logarithmic. And what that means is that a 2 on the Richter scale has 31 times more energy than a magnitude 1 does. Normally 2s are the smallest quakes that people even notice. The largest one recorded has been a 9.5 back in 1960 in Chile, where over 1,600 people died. There have been earthquakes in Hickory, North Carolina. I was in Hickory when we had our earthquake, but I was down in the basement of Minji Science in a room without windows, and I didn't feel a thing. I live in Lenore, and we had an earthquake in the middle of the night. Again, a really teeny one, and I heard it. It sounded like something had fallen, but I didn't get up to investigate. I wouldn't have found anything anyhow. And then the next day, you know, in the news, they're saying, oh, there was an earthquake. So they make a noise sometimes. All right, there are several problems involved using the Richter magnitude scale for really large quakes. And scientists now have a modified scale that they use. So let's look at the modified Mercalli scale and the Richter scale. So a 2.5 is generally not felt. A 3.5, people would feel it. 4.5, there'd be some local damage. A 6 is very destructive. 7's a major earthquake, and so on. But if we look at the modified Mercalli scale, maybe a 5 is felt nearly by everyone. Many people are awakened. Swaying trees and poles may be observed. But that doesn't have any correspondence over here to a number on the Richter scale. And again, many structures destroyed. Well, that really does depend on where you are, what kind of buildings you have. So let's look at some earthquakes in the United States. Most of the earthquakes that we hear about in the news happen in the western US. California is noted for their earthquakes, but others have happened around the country. So here's a graphic from the USGS. You'll see that if it's a red area, it's got 32 plus on their hazard level. And the lighter the color, come down here, it has. So if you live in Florida or South Texas, probably earthquakes you don't have to worry about. Charleston, South Carolina had, again, an earthquake back in the 1800s. There's even evidence of it and photos in the museum. This is that New Madrid fault that I talked about. It is noted for the earthquake that happened there, lasted for days. They say it made bells ring in Boston, Massachusetts. The ground shook so much. You can see California is just one big red blob mess. The earthquakes in Hawaii, that's what this pretty little group of colors is, are associated with the volcano. This is Alaska. This is Alaska, and again, it has a lot of earthquakes too, partly because of volcanic activity. So what are some of the effects of earthquakes? Well, the ground will shake, and if the ground shakes, buildings can collapse. It all depends on what they're made out of. Some buildings are made to withstand earthquakes. Japan has really stringent building codes. Newer buildings are designed to move with the earthquake and not collapse because they have so many earthquakes. Fires, well, the fires that are associated with earthquakes are because of broken gas lines and downed power lines, and that's why you have a fire. Landslides are common in places where the rock is easily damaged by vibrations. China happens to have a lot of problems with landslides during earthquakes. Liquefaction is something you may not be familiar with. When the ground gets soaked by water and then you shake it, the water will actually separate from the soil, and things that were buried underground will actually come up. So this is common in water saturated soils. Here's a photograph of some cracks and some mud that's come up in a grassy area. So if you have mud showing up in a place that was dry beforehand, that's evidence of liquefaction. And here these are drains going down to the sewers that have been pushed up. So let's look at the permanent displacement of land surfaces. We'll look at the permanent displacement of land surfaces. So uplift or the land dropping, that would be subsidence, can occur. It just depends on your earthquake. Ground displacement can tear a building apart. It's typically, you see it in highways. This is a photograph. And this is one from San Francisco. Here is one from Alaska. You can see the railroad ties have just been all wiggly, the railroad tracks. Let's talk about aftershocks. So earthquakes actually have usually three parts to them. There's the foreshock that occurs before the earthquake. Sometimes these are just little trembles that you're not sure the earthquake is really going to happen. Then there's the main earthquake, and then there's the aftershock. Foreshocks are almost always very small. The earthquake can be large or small. Aftershocks can be large or small. An aftershock can be almost as large as the original earthquake. They are really damaging because of the fact that your buildings were damaged by the main earthquake, and now you have a secondary earthquake coming in. And so things that were loose but were hanging on might collapse because of the aftershock. So this is why when you have an earthquake, they usually make you evacuate and they won't let you go back into your home until they've decided all the aftershocks are over with. And you can have lots of aftershocks and they can last for days. You also get tidal waves or tsunamis as a result of earthquakes if they happen near the ocean. And these can be very deadly. We've seen a graphic similar to this before, that a tidal wave, the ground shakes and so the water sets up a wave, and it's only when that wave gets close to land that friction pushes the water up, and you have these really tall waves associated with them. So in December of 2004, Indonesia experienced a 9.2 on the Richter scale earthquake. But what was so damaging was the tidal wave, the tsunami that was set up, and over 200,000 people died, not because of the initial earthquake, but because of the tidal wave. In 2011 in Japan, they had a magnitude 9 earthquake. 15,000 plus people died because of the tidal wave, because of the tsunami. This was actually the Fukushima one. The tidal wave flooded a nuclear power plant, and it created such damage that people had to just pick up and leave. They had to desert the town. They're allowed to go back, I think it's once a year, with protective gear to go and search for mementos or for loved ones. There are videos about this on the internet, and parts of it are just very sad. The Japanese are really good with earthquake damage prevention. They're really good with that, but I don't think it crossed anybody's mind that the earthquake was going to set up the tidal wave and that the combination of the two was going to be so detrimental. After the one in Indonesia and Fukushima, there's a lot more tidal wave recording stations to give people a little advance warning. There's a big system of it, especially out in the Pacific, that is so prone. So the distribution of earthquakes. Earthquakes tend to follow narrow geographic belts. So here is North America, there's Florida, here's South America, we have Africa, China's over here, this is Japan, here's Australia. So you can see the little red dots are earthquakes. And you can see that they tend to follow along, if you remember back, this is a tectonic plate boundary. Now there are others that come across. You can see, even though this is not right here is not a tectonic plate boundary, it is a belt where there's a lot of earthquake activity. So the Circum-Pacific Belt, which is sometimes called the Pacific Rim Belt or the Rim of Fire or the Ring of Fire, circles the Pacific Plate in the Pacific Ocean. And we get a lot of big earthquakes there. A second concentration is found along the Mediterranean Himalayan Belt, and that was the one I talked about going right here from the Mediterranean Ocean across to the Himalayan mountains. So the Mediterranean Himalayan Belt. You get shallow focus earthquakes around mid-oceanic ridges. You can have earthquakes associated with hot spots, like right here. This is where Hawaii is, so earthquakes associated with the hot spot. This is that Mediterranean Himalayan belt right here, cutting across. And again, we've talked about the 3 types of plate boundaries, so we won't do it again. I just wanted to remind you that that's where we are. So earthquake prediction and control. Let's talk about, can we predict them? Well, there are all kinds of monitors out to look at changes in surface elevation, to look at changes in well water, to look at radon gas emission from rocks. All of these things can foretell of an earthquake's probability. But we're not really good at predicting them. The earth has so many little cracks in it, and it's so dynamic that it's really almost impossible to accurately predict. The Chinese have studied animal behavior to help predict earthquakes. If you think about it, that's not as crazy as it sounds. I had a small dog one time that, would bark every time a leaf fell in the backyard. So animals sense things that you and I don't even notice. And so the idea is, and farm animals react differently right before an earthquake. They seem to sense a change. So scientists believe if they could just hone in on what is it the animal is reacting to. Is it changes in air pressure? Is it a vibration they feel with their feet? Is it some sort of electrical signal? Just what's going on? Once you can isolate whatever the animal is reacting to, you can build a sensor to do the same thing. They have lightning strike sensors in Florida because Florida has a lot of lightning strikes, to predict students that are out on, say, playing softball or things of that nature. And so I know maybe you've been someplace and the hairs on your arm have responded, and then there's been a lightning strike. Actually, if you can feel it with the hairs on your arm, you are too close. You need to get back to safety. But again, if we could just figure out what the animals are reacting to, we would be able to come up with some sort of a monitor. Control. Can we control earthquakes? Well, no, but we keep trying. So we are aware that if you pump liquid underground under pressure, it will actually create earthquakes. Smaller earthquakes than nature usually makes, but earthquakes nonetheless. They discovered this when they started looking at a pattern of earthquakes in the Denver, Colorado area. Denver was not noted for its earthquakes, and they were able, under investigation, to tie those earthquakes to the pumping of wastewater from a mining operation. They'd taken that water and pumped it deep underground, and that had actually triggered an earthquake. And we now know that the process that they refer to as fracking can, because it forces water, liquids underground, can result in earthquakes. And in fact, places that never had earthquakes before are now getting lots of them associated with the fracking process. Oklahoma, for example. I think I've offered a video for extra credit on this, so maybe you will watch the video. So pumping water underground creates earthquakes, and we had hoped that by having lots of smaller earthquakes, maybe you could release some of the energy and not have a big earthquake. The jury's still out on that. And that's the end of our discussion. We will stop.